Part 2 for the oscillations in simple harmonic motion video. So we took a look in video 1 at what was going on with the position of something undergoing oscillation. It has to be sinusoidal. Default is cosine graph because cosine begins at time 0 or angle 0. Cosine begins with an amplitude, which is how you have to start an oscillator. You can't let it go at equilibrium and have it do anything. It'll sit there. That's what equilibrium is. So, but you can technically write one as a sine as well. So we've got that, and we can kind of prove this idea of simple harmonic motion. We can take a look at the graphs for position, velocity, and acceleration from a conceptual standpoint of rates of change and have it match up with those formulas. But let's take a look now at the idea of a spring. How does a spring undergo simple harmonic motion, and what does that look like from an equation standpoint? And one of the reasons we want to do that is because in an activity that we did in class, we saw that if we had a spring with what we knew was a larger k value and a spring with a medium k value, if we had the same mass attached to each of them, the spring with the smaller k value took longer to complete cycles. And if we had the spring and we increased the mass on it, it increased the period. So we built up this little conceptual idea that the period of oscillation, the period it takes to go back and forth through a cycle, which on this graph would be from here to here, that's one period. If the k value is bigger, the period should be smaller, which we discussed kind of makes sense. If you have a larger k value, then you have more force acting on the mass, and more force which should cause a greater acceleration, which would reduce the time it takes to go over a displacement. Makes sense. And then the opposite was true for the mass. If you increase the mass on an oscillator, going from say 200 to 500 grams, the period took longer, at a greater period. And that again makes sense because if there's more mass, then you have the, assuming constant force, because the spring constant is not changing, more mass would create a smaller acceleration, which would take longer. So this idea of the period being somewhat proportional directly to mass and inversely proportional to spring constant is all we got. That's what we got to. So we want to show why that's true. And for that, we just need to take a look at two concepts. First, what is the spring force? And second, can we connect it to that idea of simple harmonic motion? So first off, springs are conservative forces. So springs and gravity are all we're going to deal with here. And for gravity, it's going to be pendulums. But sorry, I'm annoyed by all that stuff there. Can I get rid of this somehow? There we go. So spring force as a vector is negative kx. The displacement goes to the right, the force pulls to the left. If the displacement is to the left, the force pulls to the right. It's always trying to restore its position. So if that works, that's cool, we know that. And if we replace force, if the only force acting on an object was of the spring force, we could say that that spring force is equal to m times a. So replacing spring force with m times a, we get something that looks really close to simple harmonic motion. It's an acceleration on one side and a negative of a position on the other. Interesting. So if we expand this idea, if we just kind of run with it, we can divide both sides by mass. And I would have acceleration is equal to negative k over m times x. Now, this looks, I'm sorry, I forgot the vector hats. This looks like something that is simple harmonic motion. We've got a is equal to a negative multiple of position, but it doesn't really connect us back to that period yet. So if we take this and say that if it's simple harmonic motion, it really needs to be negative omega squared times x. And then we just take a look at these two parts together. Just take a look at the negative k over mx squared and the omega squared times x, which it's not showing up. Why is it not showing up? Oh, there it goes. If we set those two equal to each other and do some simplification, which is just a little bit of algebra, the x's cancel out, the negatives cancel out. We'd have omega squared is equal to k over m. And if we remember back to our circular motion stuff, angular frequency or angular velocity here was 2 pi over the period. So we can say that 2 pi over period squared is equal to k over m. Here's where we're approximating oscillations as a cyclical pattern, just like we had circular motion. Apologize, it seems to be not updating again. There it is. So we make that substitution, and if we process this and we do a little bit of simplification in algebra, we end up with period equals 2 pi square root m over k. And that's the period of a spring oscillator. That's the equation that pops up on the AP exam sheet. And more importantly, if we take a look at that, that's got the two properties that we needed from what we're doing in the activity. Oops, sorry. Things aren't working. That was a mistake. That mass is sort of directly proportional to period, and spring constant is sort of inversely proportional. But there's a square root and a 2 pi and all that stuff. Let's take a look at the numbers that we did have here, though. I'm going to make this smaller and see if the changes here can give us the desired change that we want. So for the spring constant, if I'm going for keeping the k constant here, and I go from 200 grams to 500 grams, that's a factor of 2.5. So if I modify my mass by a factor of 2.5, my period should be increased by a factor of square root of 2.5, which is a factor of 1.58. So at 200 grams on there, I had 0.55 as the period. If I multiply that by 1.581111, I get 0.869. Oh my goodness, that's so close. I'd say that's within a 5% error, being off by 0.006 out of 0.8. Yeah, I think that's a pretty good margin of error there. We can do the same thing here for the smaller spring constant. If I were to take that period and I were to multiply it by the increase factor here, I'd get 0.964, and I had 0.95 in reality. So this equation here seems to fit. Now I don't know what the k values were for those springs, so I can't do a comparison there. But for the increase in mass, this idea of the square root is working for us. So in order to find out what the spring oscillator period is, we would have this equation right here. Now, we have not done a lab on pendulums, but we could take a look at the two factors that are going to dictate how a pendulum would move. Pendulum is a mass on the end of a string, swings back and forth. Here, we've got gravity driving the system. There's no spring involved. And if we're going to still get this same sort of idea of A being proportional to omega squared times x, we need to figure out what the acceleration is and what the x is. But first, let's go ahead and make a little prediction here. If I had a couple of factors that might influence the pendulum period, I've got the length of this right here. And if I've got a longer string, that means I've got to cut through a bigger arc. And if I got to cut through a bigger arc, that's a bigger displacement. So a longer string should, and I apologize, let me remove the equal sign there and do a little squiggly. I would expect if the length of the pendulum gets bigger, for the period of the pendulum to be bigger as well. longer string, it's going to have to cut through a bigger arc, should take longer. But I would also expect that since gravity is driving this system, that if gravity were to increase, I'd have a greater pull, which would allow me to go quicker through my swing. So I should have something approximating an inverse relationship with the pull of gravity. So let's see if we can get to this sort of relationship using this right here. We're going to have to do a little bit of the fiddling about with the 2 pi over t as well. But in this case, if I've got a string here, I've got the acceleration of gravity going straight down. The acceleration that's going to pull it inward using similar triangles would be g times sine theta. I'll leave the omega squared there for now. And the position of the object, here I'm dropping the negative because the acceleration is kind of going to the right, but the position's to the left. We can figure all that out later. Here the position that it is sort of the arc length. If we're doing small movements, we're not going around full circles, we can approximate this right here as a straight line distance. And that would be, in terms of geometry, the arc length would be L times theta. Now, here's where we're going to get a little funky. And this is something that you don't typically do in a lot of math classes. I think whenever I talk about this, people say, what are you even talking about, Mr. Zook? If we're in radians mode, there's something called small angle approximation. And a small angle would be something like pi over 30. Okay, pi over 30 is a small number, 0.1. If I have radians of 0.1, if I take the sine of that, go to a couple digits there, it spits out almost the same exact thing. It's pretty much the same number, 0.0147 versus 0.0145. This is something that's true for all small angles, as long as you're within about 10 degrees or so from vertical, that sine of theta is approximately equal to theta for small angles. This is kind of an important thing in physics so that we can solve problems like this, but they don't talk about it in math class very often. It's just kind of one of those things that doesn't happen. So if I've got, I apologize, I've got the things not catching up again. So here, I can take that sine theta and the theta using the small angle approximation to say they're the same. Cancel them out. They're gone. Then I'll end up with G. G equals omega squared times L. And if I follow the same thing that we did before, I can say that omega squared is equal to G over L. I can replace the omega with 2 pi over t squared and do the same sort of algebraic simplification. I'll have the period for the pendulum is equal to 2 pi square root L over G. And this equation as well is posted on the AP exam equation sheet. They both are written this way, but there should be some conceptual backing there. A longer pendulum is going to cut a bigger arc, and that means it's going to take longer because it's got more distance to travel. But if you kept the length the same, if you were to have greater gravitational attraction, it should be able to pull it through in less time. And if there's less gravity, you'd expect there to be, well, the pendulum wouldn't move too quick. It'd have a larger period in that case. So that's where we can define those equations for the periods of a spring and a pendulum when they're undergoing simple harmonic motion.